Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera to everyone. So welcome to Soil Mechanics module number 2 under topic Soil Classifications part 1. In the end of this topic, the students will have a comprehensive understanding on identifying the type of soil that have similar characteristics which represents similar engineering properties. We also hope that the students can identify the importance parameters based on laboratory testing. And finally, students will be able to classify the soil according to in this topic or in this course we chose based on USCS or Unified Soil Classification System and also H2 classification system. Why we should classify the soil? Okay, the reasons why we have to classify the soil is because we want to provide a conventional classifications of types of soil for the purpose of describing the various materials encountered in site exploration. So for your information, soil particles can have varying sizes, shapes and also mineralogies. Okay, so it has a varying sizes. Okay, you have different size, have different shapes and different mineralogy. Okay, different mineralogies. So all soil may have a different size, different shapes and also different mineralogies, and these properties usually interrelated. For example, the larger particles, normally if you're talking about large particles, in terms of size, normally we know that it's big. When you're talking about shapes for large particle, it's more to rounded to angular shapes. And when talking about mineral for big particle, we know that normally for big particle it consists of quartz and asphalt. Okay? So this is for big particles. This is what I mean that they are related to each other. Okay. Meanwhile, if you're talking about small particles, in terms of its size, definitely small. So it means that it has a fine grain type of sizes. Small particles. In terms of shape, for small particles, it's like a plate-like, or flaky. And if you're talking about minerals for small type of soil, it normally consists of silica and also alumina. So this is what I mean by each of the characteristics, most likely will be related to each other. In order to classify the soil, basically classification system need to satisfy a number of conditions. For example, it must incorporate as descriptions definitive terms that are brief and yet meaningful to the users, and it also have to make sure that its classes and also subclasses must be defined by parameters that are reasonably easy to measure quantitatively, and its classes and subclasses must group together soil having characteristics that will imply similar engineering properties. Most classification systems divide soil into two main groups, which is coarse and also fine. We have coarse grain soil and we also have fine grain soil, and the grouping is actually based on texture and also size. Based on texture and size. So we group soil into two main groups, which is coarse and fine. In addition to fine grain soil, we have organic soil. So organic soil is a fine grain soil. So organic soil is a fine grain soil with sufficient amounts of organic matter. So it has an organic matter. So we have types of organic matter here. We have silt and clay and also peat. Alright, so later we discuss on that. We back to the two main group of soil. You may find that certain reference book divide soil into three main groups, which is coarse, fine and also organic, but there's also some reference book just divide into two main groups. So it is actually okay. It's just that you have to understand, okay, that what is actually the components of those groups. Okay, for coarse grain soil, we have gravel and also we have sand. For fine grain soil, okay, we have silt and clay. So what is a gravel, sand, silt and clay? It's a type of soil. So gravel and sand, okay, is grouped under coarse grain soil. Okay, the reasons why, because of why? Because come back to the texture and size. Okay, because the size is big. Okay, you're talking about size is either big or small. If you're talking about texture, it's either coarse or fine. So we group gravel and sand because it has a big particle. Okay, you have a big particles. Okay, and in terms of the texture, it is coarse. Okay, and we have also silt and clay, belongs to fine grain soil. Because of why? Because in terms of the size, okay, in terms of the size, it is small. Okay, small. And if you're talking about the texture, it is fine. Okay, and in addition to fine grain soil, we have, as I mentioned previously, you have organic soil, and under organic soil you have organic silt or organic clay, and another one is what we call as peat. So how we want to differentiate whether it is organic silt or clay? Okay, organic silt and clay. Again, remember, silt and clay belongs to fine grain soil. Okay, and another one is peat. Okay, we know that when we're talking about organic soil, it must have an sufficient amounts of organic matter. If the organic matter, okay, contains more than 75%, okay, if it has more than 75%, so means that this will be regarded as peat. If it's less than 75%, then it can be categorized either it is organic clay or organic silt. Okay, there's no organic sand, there's no organic gravel. Because of why? Organic is additional types of group belongs to fine grain soil. So it can be organic silt or organic clay if the organic matter is less than 75%. But if the organic matter is more than 75%, then we denote it as peat. Okay, so if you're talking about coarse, it's simple. Okay, if you're talking about coarse, these kinds of soil, the grains are well defined and may be seen by your naked eyes. Okay, the individual particles may vary from perfectly round to highly angular, reflecting to their geological origins. Okay, however, for fine grain soil, which is silt and clay, they have particles smaller than 60 micrometer. It means that you cannot see from your naked eyes. Okay, you can't see from your naked eyes. Okay, so if it is this one, yes, you can see. Okay, you still can see with your naked eyes from coarse, but for fine, okay, you cannot see. Okay, it's a microscopic level. Because of the wide range of particle sizes, shapes and also mineralogies in a typical soil, a detailed classification of each soil would be very expensive. So for the purpose of identification and classification in the field, a series of simple tests can be carried out. Okay, when I say that simple test, it means that you don't need to have a specific apparatus. Okay, no specific apparatus, okay, to be used. Okay, to be used in order for you to classify the soil. So no need. Okay, so what you can do is you identify the type of soil based on visual examinations and also feel. Okay, so by visually, it means that you classify the soil visually. Okay, it means that you are using your eyes and also feel. So it means that that's a very simple things that you can do. You go to the site, okay, you observe the soil at that particular area, you touch the soil, and you can have an initial guessing. Okay, you can have an initial guessing what type of soil. Okay, definitely it will not be really accurate. Okay, not be really accurate quantitatively. Okay, you can't measure it quantitatively, but at least you can have some ideas. Okay, what kinds or what type of soil, okay, that encounter at site. So what you can do, okay, is if you can, let's say if you want to identify, you can identify the main groups by visual examination and feel. For example, like if you want to know whether it is under coarse or fine, okay, so you look at the visually, you look at if you can see, okay, the grain, okay, you can see the grain, means that you can see this solid particles, you can see. As long as your eyes can see, it means that it is coarse. If you cannot see, but you can just touch and you can feel it, means that that is fine. Okay, that is in terms of particle size. Okay, and if you're talking about gradings, okay, what it means by grading? Grading is actually is another to describe another criteria for coarse grain soil. Okay, we're talking about grading is normally associated to coarse grain soil. So if you have sand and or you have gravel, you want to know whether in terms of grading it is well graded or poorly graded. Okay, poorly graded or known as uniform. Okay, uniform type of soil. So what you can do is, okay, you have to, the same thing, you have to look at the size of particle. If you found out at that particular site it has a wide range of sizes, it has a many size from big to small, it means that it is well graded. On the other hand, if you look at it only have a certain or specific size, it means that it is poorly graded or uniform, right? Okay, so come back to this one. Okay, come back to this one. I said that if you want to know that is coarse or fine, first is by visual examinations. Okay, you look, if you can see the particle, it means that it is coarse, but if you cannot see the particle, it means that it is fine. So let's say you can see the particles, you want to further identify whether it is gravel or sand. So what you have to do is to look at the size. Okay, gravel definitely has a bigger size than sand, and how big it is, we will discuss it later. Okay, if you're talking about fine, okay, because we know that fine you have silt and you have clay, so you cannot see the grain side, okay, but you can feel it. Okay, you can touch and you feel it. If let's say when you touch, okay, you rub between your fingers, you feel slightly abrasive, okay, but not gritty. Okay, you feel it slightly abrasive, but not gritty. That means that it is silt. Okay, you cannot see, but when you feel it, you can feel slight gritty feel. Okay, but if you touch and you cannot feel anything, okay, very what we call that, greasy, okay, very greasy, it means that that is clay. Okay, that is clay. Okay, and the last one is based on the compactness. Okay, compactness of field strength maybe estimated using a hand spade or pick, or driving in a small wooden peg. Okay, the soil is then reported as being either loose, dense, slightly cemented, or anything that appropriately. Next, the other criteria that can be considered in order to classify the soil easily is by depending on the soil moisture content. Okay, depending on the soil moisture content, which means that you can find out in terms of the cohesion, plasticity, and consistency. And remember, all these criteria need to be determined based on the moisture content. Okay, the natural moisture content of that particular soil. Okay, at its natural moisture content, okay, the soil, okay, is known as having a cohesion value. Okay, having a cohesion value if the material can stick together. It means that, remember, it needs to be done at its natural moisture content, not in dry conditions. Okay, if that material at its natural moisture content can stick together, it means that it possesses cohesion. Okay, if the material at its natural moisture content can be easily molded without cracking, that means that it possesses plasticity. It has that plasticity characteristic. Okay, and if you're talking about consistency, you are referring to this. Okay, either the soil is very soft, firm, very firm, hard, or crumbly. Okay, what it means by this, okay, at its natural moisture content, okay, at its natural moisture content, okay, you take a handful sample of soil and you try to squeeze between your fingers. Okay, if let's say it exudes between your fingers, it means that it is very soft. Okay, if it's very easy to mold and it still sticks to the hand, it's you try to mold, it's very easy to mold and stick to your hand, but it's not exude between your finger, that would be categorized as soft. Okay, if you're talking about firm, it means that if it still can be molded easily, but you need a moderate pressure. Okay, still can be molded. Okay, that is firm. If you're talking about very firm, it means that if still can be molded, but you need a considerable pressure. So it means that these three conditions, you can still mold the sample, but depends on the stage of the pressure being applied. Okay, and if you're talking about hard, it means that you cannot mold. Okay, this one you can no longer mold the soil. Okay, and finally, if you're talking about crumble, it means that if you try to mold, it breaks into crumb. Okay, so that is how you want to explain in terms of soil's consistency. Previously, we have been discussed on some simple tests that can be carried out without using a proper apparatus. Mean that simple testing without having a specific apparatus to classify the soil. Okay, but now we want to discuss two types of testing that need to be carried out in the laboratory for soil classification purpose. So we have one. We group into two. One is particle size analysis, and another one is ultimate limit test. Okay, for particle size analysis, we have two types of testing to be carried out at lab, which is Sieve Analysis and also Sedimentation Analysis. On the other hand, for ultimate limit test, you need to carry out two tests also, which is liquid limit and also plastic limit. Soil sample in natural condition normally has a various size, okay, of particle. Okay, so what are the definitions of particle size? Okay, when analyzing each grain, you will notice that not only they have a different sizes, but also comes with different shapes. Okay, so size and also shapes are actually related to each other. Okay, different size of grain ranging from small, okay, ranging from small to big. Okay, range from small to big particle, and different size grains subjected to different properties of soil. Those as geotechnical engineers, size of particles for each soil is very important prior deciding suitable foundation, especially for big structure. This table shows a range of particle size for different type of soil with different standards. Okay, with different standards. You will notice that there are slightly different in terms of sizes. In this topic, in most cases, the range of sizes for each type of soil will be discussed on the basis of British standard and also ASTM, but we normally follow British standard more compared to ASTM. So if you look at this table, you will see that different type of soil. Okay, we have gravel and sand. And what is a gravel and sand? It belongs to coarse grain soil group. And you also have silt and clay, which belongs to fine grain soil. Okay, and finer than that, what we call as a fines. So if you're talking about gravel, okay, for BS, the size range from 60 to 2 mm. Okay, we use the SI unit mm, and for ASTM, it's a little bit larger than that. Okay, for sand, it is less than 2, okay, to 0.06 mm. Okay, so this is the limit. Okay, this is the limit of the grain size that normally we can see based on our naked eyes. Okay, lesser than that, okay, most likely we need to use a microscope. So for sieve and clay, it has also its own range of sizes based on BS and also based on ASTM. In soil sample, we are interested to know how much of soil is the big particle and how much is the small particle presented. Although natural soils normally are mixed between various size particles, it is common to find a predominance occurring within a relatively narrow band sizes. Okay, we know that when talking about size of particle in even in small sample, you have a wide range of sample, especially for well-graded type of soil. So you have from big to small, okay, but what we are looking for is we want to try to find the dominance, okay, the dominant types of soil. So if you're talking about big to small, it means that it may have all type of soil. You have a gravel, you have sand, you have silt, you have clay, okay, in the sample of your soil. But what we are looking for is which one is the dominance. Is it gravel, is it sand, is it silt, or clay? It means that it consists the major percentage, okay, in that aspect, in that particular sample. So we want to know which one is the dominance. Okay, in classification of the soil sample, okay, there are two testing associated to particle size, okay, that need to be conducted. Okay, we have a sieve analysis and we also have sedimentation analysis. Sedimentation analysis is also known as hydrometer test. Okay, hydrometer test. So this is the boundary. Okay, so this is the boundary. Okay, the boundary of the particle size in which that it can be identified based on sieve and also based on sedimentation analysis. Okay, if you look at here, the boundary is at 75 micrometer or 63 micrometer, approximately that value. So it's about 0.075 mm and 0.063 mm. Okay, so anything larger than that, okay, can be easily measured based on sieve analysis. Whatever that lesser than that can be measured by sedimentation analysis, and these two testing, okay, is measured, okay, a type of soil based on what? Based on particle size. Remember previous slide, to classify the soil, you have to conduct two set of testing. You have particle size and you also have utterable limit. So if you're talking about particle size, you have sieve and you also have sedimentation. But those two, sieve and sedimentation, just classify the soil based on what? Based on particle size. Okay, let's discuss on sieve analysis. Okay, this method covers the quantitative determinations of the particle size distribution in a cohesionless soil. Okay, in a cohesionless soil. Okay, this may be a new term for you. What it means by cohesionless is actually similar to coarse grain soil. It's just that we use a different term. Later I will explain why we use cohesionless term. Okay. Okay, we want to determine, okay, quantitatively the particle size distribution in cohesionless soil down to a fine sand size. And testing will be conducted based on the British Standard Procedures, okay, BS 1377, Part 2, 1990. The objective of the test is to group soil particles into different range of sizes and subsequently the relative proportions by dry weight of each size, which means that to conduct this test, okay, the sample must be dry prior testing, okay, prior testing, because we want to quantitatively obtain the percentage of each type of soil for range from cohesionless down to a very sizes, okay, in a dry weight proportions. This is the apparatus for sieve analysis. Okay, test this with the following aperture sizes or the equivalent standards may be used according to this size. Okay, so what you need to do is you need to arrange the sieve. Okay, the top one will be at the bottom, followed by the small one. So the big apertures, okay, the sieve with the big apertures will be on the top, followed by the small apertures, and finally we have the tray here. Okay, we have the tray here. Okay, here are the procedures to carry out sieve analysis tests. Okay, what you need to do is, okay, this is the first step. Okay, you need to weigh a dry sample, okay, to 0.1% of its total mass of about 200 grams. So your sample must be in dry, and this is at about 200 grams. Okay, it's about 200 grams. Don't be too accurate. Okay, it's about, okay. And then fit the largest size to sieve appropriate to the maximum size of the material, present to the receiver, and place the sample on the sieve. Okay, and what you need to do before you shake, that you need to ensure that you have screw everything with the lids, and then you shake the sieve set using a suitable mechanical shaker for about 10 minutes. Okay, about 10 minutes, and then weight the amounts of retained material on each sieve to 0.1% of its total mass. So very simple test. Okay, very simple test. You take the sample in dry conditions, about 200 grams, put on the top of the sieve. Okay, remember you have to arrange first. Make sure the top aperture should be on the top, followed by the small aperture, and then make sure it's tightly screwed. Okay, press the shaker, shake the sample into within 10 minutes, and then you weigh the sample that retain means tertahan, retain on each sieve. Okay, this is the example of data recorded and calculated after carry out sieve analysis test. So to calculate mass passing, okay, mass passing is simply total up the mass of retain, okay, the mass of retain for each sieve, then minus with mass of retain for each sieve respectively. Okay, so I'll explain it one by one. Okay, the one that you record is actually these two. Okay, you have the lab sheet, you have the sieve size and mass retain. So you already this one is depends on your sieve. Some of you might not use this size, might use different size. Okay, it's okay. So whatever size that you use, okay, just record it here. Okay, record it here. And remember, in the end of the testing, okay, you weigh the mass retained on each sieve. Okay, let's say your soil sample total up is 200 gram. Okay, the 200 gram. So what you need to do is you need to weigh, okay, on each sieve. Okay, so each sieve for sieve 10, let's say there is no particle retain on that. If there's no particle retain on sieve number 10, means that, okay, this is your sieve number 10, right? Sieve number 10, okay, it has its own aperture. Okay, we want to look at the particle that retains here. If you look at this example, the particle that retain on sieve number 10 is 0, which means that nothing here, everything passing through sieve number 10, right? So followed by sieve number 63 to until the final one, 63 micrometer. And you have to make sure that when you total up everything here, it must be at least, okay, the difference not more than 1%. So it means that total up, initially you put 200 grams, make sure you got 200 grams as well, or not, the difference not more than 1%, less than 1%. If let's say the difference is bigger than that, what you need to do is to retest it again. Okay, retested it again. So there's two, okay, the mass passing and also mass passing, the percentage of passing is the one that you calculate, okay, from the data that has been recorded here. Okay, so how to calculate the mass passing? Okay, we know that the total, let's say after that the total is 200 grams. So that 200, okay, minus, okay, here because it has 200, because it has 200 is here, supposedly to 200 minus 0, it is 200. So 200 minus 15 equal to 185. 185 minus 36.7 here, and followed by the rest of that. So how to calculate the percentage passing? Okay, you look back, whatever that passing here, mass passing here, divide by total here, 200 times 100, you got 100. Okay, here 185 means that 185 divide by 200 times 100, you got 93, and followed by the rest. Okay. Okay, once you finish everything, you already calculate everything. Okay, the data that you need for further analysis is only percentage passing and also sieve size. Okay, so moving here, you need to plot the data that you obtained just now, sieve size and also the one that you've been calculated, percentage passing, and analyze it, okay, with particle size distribution graph. So this is this graph, we call it as particle or grain size distribution diagram. Okay, so your y-axis is percentage passing and your x-axis is sieve analysis. Okay, remember last time, if you look at sieve number 10, percentage passing is 100%, so you have 100 here. Percentage at 6.3, below that, first 10 mm, and then if I'm not mistaken, 6.3 mm, about 93% if I'm not mistaken. So where's the 6.3? Okay, remember this is log size graph, log scale graph. So you need to rearrange the scale here. It's log 10. So for example, look at your size. Which one is the final? Just now is 0.063. So you start with 0.01 times 10, it becomes 0.1. You 10 times 10, it will be 1 here. Again, times 10, you got 10 here. Alright. So what you need to do, for example, like if you want to find size 6.3. So 6.3, where is 6.3? This is 2, 3, 4, 5, 6. Okay. So see here, 6.3 is maybe somewhere here. And for 6.3 size, about 63 particle passing, right? So here, go down, it's 93. And followed with the rest. Okay, and another thing that you have to remember, if you look at this one, I connect each of point. Okay, this is the curve. It's curve, not straight line. But it is not necessary to connect each point. Okay, it is a best fit curve. Okay, so you can just plot like this. Okay, it's not necessary to. Okay, and the curve is somehow like S curve. Alright. And the position of a curve that you get from the grain distribution diagram, okay, indicates the fineness or coarseness of the grains. Okay, the higher and the further to the left curve, the finer grains. Okay, so the higher the curve to the left, okay, near to origins, it means that it indicates that it is a fine particles, and the other way around. Okay, if it's the curve is higher to the right, it means that it is coarse. This is also depends if you arrange your size from small to big. If you reverse it, means that maybe this is big, from big to small, so it will become the other way around lah, right? And in addition to that, the steepness or flatness and general shape also indicate the distribution of grain size for a given soil. Okay, for example, you can identify in terms of grading. Okay, remember when we mentioned about grading, we have well graded and uniform. Uniform also known as poorly graded. And you need to understand what is the what call that the definitions of well graded. Okay, well graded is covers a wide range of particle. Meanwhile, uniform graded, it covers only a certain range of size particle. So if you look at here, okay, for well graded, from big particle to small particle. If you're talking about uniform, it only covers a certain sizes only. In this case, it covers only on sandy size. So from that curve, okay, on your particle size distribution diagram, you can easily identify. Okay. And additionally, results of grading tests can also be tabulated using geometric properties of the grading curve. These properties are called grading characteristics. First of all, 3 points are located on the grading curve. Namely, you have D10, D30 and D60. What is that? For example, D10 means the maximum size of the smallest 10% of the sample. So what you need to do, okay, this is percentage of particle passing. You want to find D10. For example, you want to find D10. Go to the 10%. Okay. Move to your curve and go down to the size here. This is your D10. And what is D10? Is the maximum size of the smallest 10% of your sample. The same thing for D30 and also D60. And from that, by using these two equations, CU, what is CU? Coefficients of uniformity. And CK, also known as CC, but we normally use CK, is coefficients of curvature. So using these equations, we will identify, okay, based on the equations, okay, either the soil is well graded or poorly graded. But as I mentioned previous slide, without having to calculate these two parameters, also you can easily identify from the curve, okay, either it's well graded or poorly graded. But if you want to further prove, okay, with the values, then you have to provide these two values based on CU and also CK. Okay, previously we have discussed that particles smaller than 63 micrometer or 75 micrometer cannot be sieved, as small particles carry charges on the surface. So it has a tendency to stick together even with sieve. Okay, if you try to sieve, okay, a smaller particle lesser than 75 or 63 micrometer, it has the ability to stick. Because of what? This is the boundary of coarse and fine. Okay, what is a coarse? Coarse, you have gravel and you have sand. For fine, you have seed and you have clay. So whatever finer than this is actually belongs to what? Belongs to fine particle group. Okay, fine grain soil group. So this fine grain soil group, okay, they have contains a particle that have charges where they have the ability to stick together. So by doing sieve also, maybe we are quite difficult to separate it. So quite difficult also to get its individual particles. Therefore, the other methods based on particle size, okay, to determine, okay, and to classify the soil is by using sedimentation analysis, also known as hydrometer test. So the behavior of small particles in liquid suspension that have a tendency to settle down due to multiple forces acting on them is known as sedimentation. So sedimentation analysis is based on Stokes' law, okay, which relates the velocity of a free-falling sphere to its diameter. So we're using these equations, okay, using this equation. As the soil particles settle out of the suspension, the specific gravity of the mixture will reduce. Okay, the procedure is quite straightforward, where the soil is mixed. Okay, so this is your soil. It's mixed with a dispersing agent. Okay, dispersing agents. And then you have to stir it vigorously and allow it to settle to the bottom of measuring cylinder. Dispersing agents are added in the analysis to increase the interparticle repulsion. So remember, for these kinds of particle, for fine particle, it has the ability to stick. So that's the reason why we have to put dispersing agent to deflocculate, okay, the individual particle, the aggregations. Okay. Okay, with that, we stop for a while. I'll see you later on second part of this topic. Thank you very much.